Okay, so here we have a simple Mathematica page. So the n in front here is Mathematica's code for telling me the number. Otherwise it'll just tell me what log of, what did I put 5? It'll tell me what log of 120. It'll just say log of 120. I say give me it to 10 decimals or 10 significant figures. Here's the x, ln x minus x, and then we tried for n equals 5, and we saw that the function, the true logarithm is 4.787, and the approximation gives 3.047 with a difference of 1.74. So what do you think about that?
So it's not great right now.
Okay. Why?
Well, the difference is like half of the approximation.
Okay.
So it's not.
What, from the picture we drew, did we expect it to be good in the beginning?
No.
All right.
Because we have larger errors.
And the other thing, of course, is that we don't need to really usually find approximations for 5 factorial. You know, why not?
Because we know what 5 factorial is. It's 120.
Okay, so put in a number that you don't know off the top of your head, but it's not like, 5 billion or something.
I think 100.
Okay.
We don't know 100 factorial right off our heads. We could probably calculate it. It would be very large, but... So, this is a better approximation.
Okay, why do you say that? The error is larger.
But we have... So we have much larger numbers. Like we have log of 100. It's about...
Log of 100 factorial.
Log of 100 factorial is 363. Our approximation says it's 360. So it's an error of 3, but the terms are in the 300s, so it's a better error percent, I guess.
Okay, cool.
Maybe if we go bigger, we could go up to 10,000.
Yeah, now 10,000 factorial is going to be a number that's just absolutely gigantic.
You can't calculate it.
Well, I mean, obviously Mathematica is able to calculate it.
It's not a useful use of time to calculate it.
Yeah, it takes a lot of time. Let's see what we get here for our approximations.
So log of 10,000 factorial, I guess, is about 82,000. Our error approximations basically 5.5 off.
Yeah.
And in this scale, it gets even better. Even though the error terms are getting bigger, the terms are getting bigger much quicker.
That's right. So here we're actually getting this very simple approximation, x ln x minus x, is becoming a remarkably good approximation later on. So let's just try one last one.
Let's go up and go to 1,000,000.
Okay, 1,000,000 factorial. So here's something we would have, next to no shot calculating if we wanted to.
So we basically have it to 6 decimal places in scientific notation.
Yeah, so it's 10 to the 7th, so that's going to be 10 million. So this is 12,815,000 is the logarithm of 10 million factorial, million factorial.
And we're only off by roughly 8.
Yeah. And it turns out, so this very simple approximation is great if you need to compute the logarithm of a factorial. And it turns out there's an even better approximation that's not that much more complicated. And I'll go to the Wikipedia page here for Stirling's formula. So this is the Wikipedia page for something called Stirling's approximation. And that's where De Moivre shows up, that I was surprised by. And I'll just go through this super quick, because I assume we're going to see n ln n minus n show up in here. Did I already miss it? Oh, there it is. Yeah, you're right. N ln n minus n. So there's the first approximation. And then there's a series of sort of correction terms after it. Here's the first correction term. And I thought I saw down here n factorial is approximately root 2 pi n times n over e to the n, and then with these error terms, which is also remarkable. And then here they are, this is what I was remembering. Log of n factorial is approximately n ln n minus n plus 1/2 ln 2 pi n plus 1/12 1 over n. So this term we could have added on to shrink our errors even more. And then this term we would be starting to get right at, we were looking at 10 million, or no, sorry, 1 million. And that would be 12 million. Oh, my phone's ringing, so we got to end this now. But okay, good job, hun.